Let's do some problem solving about derivatives in calculus. In this video, we're going to focus on the derivative at a point instead of the derivative as a function. That will come in the next video. Number one, let f of x equal x cubed for part A, and we've got some other functions for parts B and C. We're using the limit definition of the derivative to find derivatives. In part A, it's f prime of 2. So let's use the limit definition of the derivative. You need to remember what that is. F prime of 2 would be the limit as h goes to 0 of f of 2 plus h minus f of 2 all divided by h. If we were after f prime of 3, it would be the limit as h goes to 0 of f of 3 plus h minus f of 3 all divided by h. This is interpreted as the slope of a tangent line. That interpretation will come out in some other problems in this video. So now it's a matter of using the function's formula. The formula here for part A is x cubed. It's a big place where people make mistakes right here. They don't quite understand what this notation really means. They see something like this and they think, well, what is f? Is f a number or something? And they think maybe f of 2 plus h is the same as f of 2 plus f of h or something like that. No, that's not what this means. F is a function. It's the name of the function. When you see a formula like this, f of x equals x cubed, whatever's inside the parentheses here, no matter how complicated it is, gets replaced. You use that to replace x in the expression. So, for example, f of 2 plus h is 2 plus h quantity cubed. I need to cube that whole thing. Another place where people make mistakes is they think that 2 plus h quantity cubed is 2 cubed plus h cubed. That's not right either. We need to figure out what that is. We'll come back to it. What's f of 2? F of 2 is 2 cubed, which is 8. And then we all divide that all by h. Now, as far as the numerator goes, you can expand that quickly with something called the binomial theorem. I'm not going to assume you know the binomial theorem. Let's just go ahead and write out what 2 plus h quantity cubed means. 2 plus h times 2 plus h times 2 plus h. So I have to do that multiplication there. 2 cubed is 8, all divided by h. Take it step by step. Multiply, say, the first two expressions, 2 plus h times 2 plus h. I have to use the good old friend FOIL method. First times first, outside times outside, inside times inside, and last times last. When I'm multiplying two binomials like this, first times first is 2 times 2 is 4. Outside times outside is 2 times h is 2h. Inside times inside is also 2h. 2h plus 2h is 4h. And then last times last is h times h is h squared. So I get an h squared. Don't forget that you're also multiplying that by another factor of 2 plus h. We're subtracting 8 and then again dividing all by h. Expand this out. I can't FOIL anymore because this is a trinomial here, 3 terms, but what I can do is effectively use the distributive property like this. Take the first term over there, 4, and multiply it times each term here. 4 times 2 is 8. 4 times h is 4h. 4 times h right there. Then go to the next term here, 4h. Multiply it times each term here. 4h times 2 is 8h. And then 4h times h is 4h squared. And then go to the last term here in the factor on the left, h squared, and multiply it times each term here. H squared times 2 is 2h squared. And then h squared times h is plus h cubed. Don't forget your minus 8. And then divide that entire thing by h. If you combined all these things before canceling the 8's, you'd get 8 plus these two combined to give you 12h. These two combined to give you 6h squared and an h cubed. We are subtracting 8. It can cancel with this h, with this 8, and this 8. Every other term up here has a factor of h. That can now be factored out, like this. Get an h there. 12h, when I factor out an h, leaves me with a 12. 6h squared, when I factor out an h, leaves me with a 6h. And then h cubed, when I factor out an h, leaves me with an h squared. You can now divide out the h. I need to explain that step a little bit. and get the limit as h goes to 0 of this expression. And then finally you can plug in h equals 0 to get 12 plus 0 is 12. The value of the derivative, f prime of 2, is 12. This is the definition of the derivative. Now, technically speaking, there's some subtleties going on here in these last couple steps. Technically speaking, in the second to last step, there is the fact that the limit of the function is independent of what happens when h actually equals 0. We are letting h get arbitrarily close to 0 without actually equaling 0 in the definition of a limit. And so that's why it doesn't matter that we can cancel the h's here. These two expressions that you see here and here are equal as long as h is not 0. So if this expression has a limit as h goes to 0, so will this, and they will be the same. That's based on the fact that in reality, it doesn't matter what happens when h is 0, because this thing is undefined at 0. This last equality, technically I plugged in h equals 0 at the end because of something called continuity. This is a continuous function of h for all h, including at h equals 0. To evaluate the limit, I can actually plug in h equals 0. So some subtleties going on there. They go on in parts B and C as well, though I won't re-emphasize them at the end. Well, or maybe I'll just emphasize them briefly. All right, part B. Now f of x is 1 over x squared. We want to find f prime of negative 1, once again using the limit definition of the derivative. For part B, f prime of negative 1. It's, in the abstract, a similar kind of limit, except use a negative 1 instead of a 2. Limit as h goes to 0 of f of negative 1 plus h minus f of negative 1, all divided by h. So in the abstract there, it's the same kind of idea, but it is a different function. It's now 1 over x squared. This is the limit as h goes to 0 of 1 over, this entire thing gets squared, negative 1 plus h quantity squared, minus, plug in negative 1 into this function, you get 1 over negative 1 quantity squared, which is positive 1. This is a 1, all divided by h. There's various ways you can try to simplify this limit. What I would recommend doing to start with is to multiply the top and the bottom by the same thing, so you're not changing the expression, you're multiplying by 1. And that the top and the bottom, I'm going to pick to be the denominator that you see here, negative 1 plus h quantity squared. To get rid of the fractions within fractions is my goal here. I have to distribute it through the top. It will completely cancel with the negative 1 plus h quantity squared there to get rid of that fraction within the bigger fraction. It's still kind of a complicated looking expression, but at least I don't have fractions within fractions here anymore. So I will get, again, cancellation there, leaving me with a 1. It doesn't cancel there, so I have minus negative 1 plus h quantity squared inside parentheses. The bottom gets more complicated, but that's okay. Like that. Now simplify the top, just keep simplifying. I got to expand that out. Don't forget to use parentheses here. I'm going to FOIL again. Negative 1, doing it in my head here, times negative 1 is positive 1. Negative 1 times h is negative h, and I have another negative h, give me negative 2h. And then h times h is h squared. So I FOILed in my head there. And again, don't make the mistake of forgetting the parentheses there in the top. You are subtracting that whole thing. You need to distribute the minus sign through, and that'll make the 1's cancel on top, and you'll get a plus 2h minus h squared, out of which a factor of h could be factored, like this. Okay, I did a couple steps there. Again, I canceled the 1's. I distributed the minus sign through first before canceling the 1's. Positive 2h minus h squared, factor out an h, get an h, times in parentheses 2 minus h. Now divide out the h's just like before. It doesn't matter what happens when h equals 0. What's left is technically undefined at h equals positive 1. It's not continuous at h equals positive 1, because you'd be dividing by 0, but at h equals 0 it is continuous. You can evaluate this limit now by plugging in 0 to get 2 minus 0 over negative 1 plus 0 quantity squared. 2 over negative 1 squared is 2 over 1 is 2. The derivative here, f prime of negative 1, is 2. Last example involves a square root. Part C, let f of x equals square root of x. Again, use the limit definition of the derivative to find f prime of 4 now. So now we've got a square root involved. Once again, the limit definition of the derivative is the same. The limit as h goes to 0 of f of 4 plus h minus f of 4, all divided by h. But now it's the square root function. This seems tricky. Square root of x there. So I need to take the square root of 4 plus h minus the square root of 4, which is 2, all divided by h. Do not make the mistake of thinking this is the square root of 4 plus the square root of h. It is not. That is not a property of square roots. I cannot simplify this thing. I can simplify that, of course, to be 2. So what do? This doesn't seem very easy. I mean, maybe your teacher will let you approximate this derivative by letting h be really, really close to 0 without equaling 0. But I want my students to learn how to do this kind of thing symbolically. What I'd recommend doing is a little trick, just like we used the trick up here. Multiplying the top and the bottom by the same thing, which effectively means you're multiplying the entire fraction by 1. Doesn't change the expression. Pick that same thing to make the top of a square root go away. Rationalize the numerator. You may be more used to rationalizing the denominator, but we're going to rationalize the numerator. And the thing to pick here is square root of 4 plus h plus 2. You might call that the conjugate of the top. And you might wonder, how is this going to help? I mean, what in the world is this going to do? Isn't this just going to make it worse? Well, it does have the benefit, it seems, of getting rid of the square roots on the top, because when you FOIL out the top, what ends up happening, because I have a minus sign there and a plus sign there, is that the outside and inside terms cancel. And first times first, the square roots go away and just leave me with 4 plus h. And last times last is negative 2 times positive 2 is minus 4. The top becomes simpler. The bottom becomes less simple, but it's still a good idea. The 4's cancel, leaving you with this. The h's divide out, and what's left, divide the h's out to leave a 1. You know, when you cancel the 4's, 4 minus 4 is 0. When you cancel the h's here, or divide them out, you get a 1. You're left with this limit, as h goes to 0, of 1 over square root of 4 plus h plus 2. And that is continuous at h equals 0. You can now evaluate this limit by plugging in 0. Square root of 4 is 2, of course, and then 2 plus 2 is 4. This is 1/4. F prime of 4 is 1/4. Number 2 is about the geometric interpretation of derivatives in terms of slopes of tangent lines and then using tangent lines to approximate functions. Suppose f is a function with f of 10 equal to 5 and f prime of 10, the derivative of f at 10, equal to 2. Part A, find the slope-intercept form of the equation of the tangent line to the graph of f at the point where x equals 10. All right, so when you want to try to find the equation of a line, you need a point on the line and you also need the slope. The point comes from the fact that f of 10 equals 5. The point 10 comma 5 will be on the line. And the slope comes from the derivative. The derivative tells you the slope of this thing called the tangent line. Now, I don't have a formula for f, so I don't know what its graph looks like exactly. But I can say that when x equals 10, y equals 5, and the slope of the tangent line near this at this point will be 2. I'm going to draw a line here. That does not mean the graph of f is this line. This is not necessarily the graph of f. This is the slope of the this is the tangent line. Tangent line to f at the point 10 comma f of 10, which is 10 comma 5, and its slope is f prime of 10, which is 2. So what does that mean? What does the graph of f look like? This is if f is nice, at least, a nice function, I haven't explained what that means. If f is nice, not too ill-behaved, a well-behaved typical function, this tangent line is a good approximation to the graph of f near this point. F itself could be concave up, it could be concave down. There are different possibilities. Let's just say it's concave up. the graph of f itself might look like that. The tangent line is approximating the graph of f near that point. Now, tangent lines can be easily misunderstood. Some people say, oh, tangent lines just touch the curve at one point. That's not correct. It only works simply that way for circles. But the graph of f certainly could come back down again and cross the tangent line again. It also can be misleading to think it's just describing it as touching it at one point, okay? A more accurate description, though still not completely precise, is that this is the best linear approximation to the red graph near this point, meaning if you zoom in closer and closer to that point, the red graph will look more and more like the green line, okay? If the graph of f is nice, not specifying what nice is, it will look more and more like a line the closer you zoom in to any point. All right, so that's the setup. As far as finding the equation, you could use initially point-slope form, and I do that here, though I do it in a way that's maybe not typical. I'm going to write f of x, or let's write L of x for the function name for the tangent line. This is going to be the tangent line here. Tangent line function, you could call it, or formula, is f of, I'm going to write the abstract form here, f of a plus f prime of a times x minus a. And maybe you'd prefer, instead of writing L of x, maybe you'd prefer just writing a y. Maybe that's the way your teacher would write it. If you subtracted f of a from both sides of this and you had it as y minus f of a equals this, that would really be point-slope form right away. But I'm writing it in a form, you could call this a linear approximation, that is most often used. And what is a? A is the value of x that you are thinking about. In this case, it's 10. The 10 is the a, okay? So for our problem, this becomes y equals L of x, and again, the L of x is optional, is f of 10 plus f prime of 10 times x minus 10. Plug in the numbers. F of 10 is 5. F prime of 10 is 2. So there is an equation for the line. It's not quite in slope-intercept form yet because I need to simplify it, essentially, is the reason. So this becomes 5 plus, distribute the 2 through, 2x minus 20. And in slope-intercept form, we could write y equals L of x equals 2x minus 15, a line with a slope of 2 and a y-intercept of negative 15. So it would be way down here. This graph is not accurate. Okay, that's the equation of the tangent line in slope-intercept form. Part B, use the tangent line to estimate f of 10.5 and f of 9.8. Okay, so we're going to use this green line to approximate the red curve. Use this equation to approximate the unspecified equation for f, effectively. It's actually easier to not use the slope-intercept form in simplified form. It's actually easier to use this form of it for part B. Why? Because usually when you're doing these kinds of problems, you have changed x slightly from a. In this case, 10.5 or 9.8 are slight changes of x from a equals 10. And when you do that, that makes this a little easier to use because you're subtracting 10, getting small numbers here that you could even easily multiply in your head, times 2 in this case. So f of 10.5, let's go ahead and use an approximately equal to sign as approximately L of 10.5. And if I plug into this equation, use an equal sign now, I get 5 plus 2 times 10.5 minus 2. That's 0.5. 2 times 0.5 is 1. We get 5 plus 1 is 6. That would be the answer there. F of 9.8 is approximately L of 9.8. That'll be 5 plus 2 times, in parentheses, 9.8. I see I made a mistake here. It's a 10. 9.8 minus 10. And that is negative 0.2. 2 times negative 0.2 is negative 0.4, so I get 5 minus 0.4, and that is 4.6. So the answers are 6 and 4.6. Before I go with this on to the next problem, I should emphasize another way to think about this. Let's go back to the general equation here. Another way to think about this is to think about it in the point slope form. Y minus f of a equals f prime of a times x minus a. And to think of this as the change in y and think of this as the change in x. So the equation becomes delta y equals f prime of a times delta x. Along the tangent line, this is how much y changes when you know the change in x. It's the rate of change, the derivative, times the change in x. So for example, for f of 10.5, if x changes from a equals 10 to 10.5, the change in x is 0.5. F prime of 10 is 2. 2 times 0.5 is 1. Therefore, the change in y is 2 times 0.5, 1. That's what we found down here. That was the change in y right there. So the value of the function changes approximately from 5 to 6. It increases by approximately 1. This is the exact change along the tangent line itself. It approximates the change in the function value with the general function that we started with. This problem is a quicker problem to emphasize the geometric meaning of the derivative. Use this figure to fill in the blanks of the following statements about the function f at the point P that you see there, that is specified. F of blank equals blank, and f prime of blank equals blank. Now, this bluish graph is the graph of f. The black line is the tangent line that you see here. This point is not on the graph of f, so this point cannot be used to fill this in. It's at the point P. We are focused on the point P. We know that's both on the graph of f and the tangent line. Therefore, f of 3 equals 4. We do need both points, though, for the second one, for the statement about the derivative. We know the derivative gives us the slope of the tangent line at this point. The tangent line is specified, and 2 points on the tangent line are specified as well. We can figure out the slope of the tangent, and that will tell us what to fill in here. Slope of the tangent is, you could write it as change in y divided by change in x along the tangent line. Look at your 2 points. The change in y is 4 minus 4.2, and the change in x is 3 minus 2.9. This is negative 0.2 divided by 0.1. That is negative 2. That's the slope of the tangent. That is the value of the derivative when x equals 3. F prime of 3 equals negative 2. That's a quick problem. Number 4 is a pretty important problem to interpreting functions geometrically and derivatives geometrically. We consider this graph of a function f shown. Part A, show how to represent the following quantities on the graph. Number 1, f of 4. Okay, that's just a function value, nothing to do with calculus. If I go to x equals 4 and go up to the graph, about there, the second coordinate of that point is f of 4, meaning then if I go over to the vertical axis, f of 4 is right about there. Okay, so that's the geometric interpretation of f of 4. Number 2, f of 4 minus f of 2. Well, what is f of 2? It's the second coordinate of this point. It's the value right about here. F of 4 minus f of 2, in this picture, f of 4 is bigger than f of 2. That, therefore, is a positive number that represents this distance here. This is f of 4 minus f of 2. If f of 4 were less than f of 2, I'd have to interpret the distance as the absolute value of this. But fortunately, f of 4 is bigger than f of 2 here. Number 3, f of 4 minus f of 2 all divided by 4 minus 2. That's a rise over a run. That's a slope. What's it the slope of? Well, not the curve itself, but the secant line to the curve connecting these 2 points. I could draw the secant line like this. That's not a tangent line, it's a secant line connecting 2 points. Its slope is equal to this expression. I could also draw a right triangle in here to emphasize that. Rise over run, f of 4 minus f of 2. I guess I'll also write that over here. Divided by 4 minus 2, that's this distance right there. The slope of this line is equal to what you see in 3. 3 is the slope, rate of change along the secant line, which is also called the average rate of change of the function f. when x increases from 2 to 4. It's not the same as a tangent line. It's not the same as an instantaneous rate of change. The instantaneous rate of change is the derivative, which is part 4. Let's use a different color here. F prime of 3, as we've emphasized in the last couple of problems, the derivative gives you the slope of a tangent line. The tangent line here is the best linear approximation to the point. It's the line this curve looks more and more like as you zoom in on this point. It would look about like this. It's, yeah, right about like that. Part 4 is the slope of this thing. The green one's a secant line. The red one is a tangent line. Secant line between x goes from 2 to 4. Tangent line at the point where x equals 3. Part B of the problem says, in each case, decide which is larger, f of 3 or f of 4. Let's write the answers over here. Well, the function's increasing, therefore f of 4 is larger. Okay, because the second coordinate of this point here is bigger than the second coordinate of this point right there. F of 3 would be right around there. 2, f of 3 minus f of 2 or f of 2 minus f of 1. That's a bit more subtle. F of 3, okay, I could go ahead and draw it. The drawing can be misleading though. Got to be careful. F of 3 minus f of 2 is this distance here. F of 2 minus f of 1 is this distance here. It does look like in the drawing that f of 3 minus f of 2 is bigger. Is that really accurate? Did I draw it accurately enough? It's accurate enough because this graph is what's called concave up. The slope is increasing. The function f is increasing faster and faster as x increases, and that means for bigger values of x where x increases by 1 unit, you're going to get a bigger difference than for smaller values of x where x increases by 1 unit. Here x is increasing from 2 to 3. What's the change in the function value? Here x is increasing from 1 to 2, and this difference represents the change in the function value, which again, this distance is f of 3 minus f of 2. This one is f of 2 minus f of 1. F of 3 minus f of 2 is bigger. Again, the key reason is because the graph is concave up, the slope is increasing. 3. F of 2 minus f of 1 all divided by 2 minus 1, or f of 3 minus f of 1 all divided by 3 minus 1. Careful, we're not doing f of 3 minus f of 2 divided by 3 minus 2. You got to be careful here because of that. These are slopes of secant lines, just like in thinking about the slope right there. F of 2 minus f of 1 all divided by 2 minus 1 is the slope of this secant line. F of 3 minus f of 1 all divided by 3 minus 1 is the slope of a secant line looking like that. You can see that one's a bit bigger. This is the bigger answer. The reason is, again, because the graph's concave up, keeps getting bigger and bigger slope, and that makes this secant line here have a bigger slope than this secant line here. F of 3 minus f of 1 all divided by 3 minus 1. Last part, which is bigger, f prime of 1 or f prime of 4. F prime of 1 is the slope of this tangent line. F prime of 4 is the slope of a tangent line about like this. You can definitely see that one's got a bigger slope. The graph, again, is concave up, so f prime of 4 is the bigger one. Our last problem is an applied problem for which we will need technology. The atmospheric pressure, P, at a point h kilometers above the surface of the Earth, so imagine the surface of the Earth, you go up into the sky a ways, maybe you're in a hot air balloon, is given by this formula here. P equals f of h equals 760 times e to the negative 0.14 h. Torr is the strange kind of units for pressure here. Sometimes units could be in pascals or in atmosphere, I think is the other unit people often use. Torr is another kind of atmospheric pressure unit. Goals are to estimate f of 2 and f prime of 2 with your calculator and say, what do your answers tell you about the pressure? Okay, so f of 2 itself, this is just a plug into the function problem, is 760 times e to the negative 0.14 times 2. It's going to be negative 0.28 torr. Probably best to approximate that. We are estimating it. That is asked for here. 760 times e to the negative 0.28. E to the 0 is 1. E to a negative power is a little less than 1. 760 times something a little less than 1 is a little smaller than 760. 574.4. 574.4 torr. That's telling us 2 kilometers up into the sky, the pressure is less than at sea level. If h is 0, I'm assuming it's sea level, then e to the 0 is 1, 760 times 1 is 760, the pressure would be 760. The pressure is smaller than at h equals 0, for example. More generally, you can say pressure is a decreasing function of height. It is exponential decay. That's an exponential decay function. Its graph is decreasing. It's also concave up. 760 right there. When h equals 2, the function value is down to 574.4 torr. You could also say, probably better to say, pressure is a decreasing function of h, of height. Okay? But this also gives us a specific value when h equals 2. Is it accurate? You know, you'd have to measure it to see if it's accurate or not. This is a mathematical model. It's probably not perfect. F prime of 2. Should I use the limit definition? Should I use something called the chain rule, which I'm not assuming you know? No, let's approximate it. It's technically a limit as h goes to 0, like in the first problem in this video, of f of 2 plus h minus f of 2 divided by h. Let's approximate it, say when h is 0.001 to be played safe. We could try 0.1 or 0.01. I'm going to try 0.001. Maybe your problem gives you extra directions to say how to approximate it. Let's go ahead and approximate it like this. F of 2 is the 574.4. What's f of 2.001? 760 times e to the negative 0.14 times 2.001 is going to be slightly smaller than 574.4. There it is. Maybe I should probably use more decimal places here. So we're going to get 574.315. I'll go ahead and use all of them. 2337 minus f of 2 was this, 574.3956435, all divided by 0.001. I'm plugging in that value of h. So let's subtract 574.3956435, that number right there, to get a small negative number. Divide that small negative number by positive 0.001, and I get approximately negative 80.4. It's important to use units here. Units for the derivative are always units for the dependent variable per unit of the independent variable. In this case, torr per kilometer. This would be negative 80.4 torr per kilometer. What does it mean? Well, one thing it means is that geometrically, when you are at h equals 2, the slope of the tangent line is negative 80.4. More importantly, it means that when you are 2 kilometers high, the rate of change, you could say instantaneous rate of change, of pressure with respect to height, the dependent variable p, with respect to, I'll just abbreviate, height h, is about negative 80.4 torr per kilometer. Now I'm not going to write anything else down, but let me just verbally say something. That's a 0 there. Negative 80.4 torr per kilometer. I'm not going to write anything else down, but let me just say, what does this mean? This means, for example, if you go up a little higher, from 2 kilometers to 2.1 kilometers high, say, that you would expect the atmospheric pressure in that case to go down by approximately 8 torr. Take that negative 80.4 and multiply it times the change in h.1, and you get about negative 8. This would be negative 80.4 torr per kilometer times 0.1 kilometers, about negative 8 torr. The pressure would go down by about that much. It's an approximation. It's not perfect. We're using a tangent line to approximate the green graph, which is concave up. It would give you an approximation a little bit too small because of that, but that is how to interpret it. This is actually much more important for interpreting calculus than you might imagine. Very, very important. Thanks for watching.